Okay, so welcome back to our session on dynamical systems. Thank you all for coming. We have a very tight schedule, so we have 6 speakers total. Each one has a block of 15 minutes, and we will try to stay on a schedule. So in particular, I will signal to the speaker 2 minutes before the end of that block that the time is about to end, and then, well, hopefully we'll manage to get the next talk started in time. Okay, so it's my great pleasure to introduce the first speaker, Roberto Castorini, who will speak about quantitative statistical properties for partially hyperbolic systems.
Okay. Thank you very much for this nice introduction, and I'm really glad to be here. And today I'm going to talk about joint work with Carlangelo Liverani. And since I have a little short amount of time and I'm the first speaker, I would like to say a few words, introductive words about what are the words in the title, and I'll try to explain very roughly what are the main results that we got. So let me say some word about the statistical properties of some dynamical systems. Imagine that you have a dynamical system which is described by a map, half from a compact Riemannian manifold here, and you expect that the dynamics has a chaotic behavior somehow. So you would like to do some parallelism with a sequence of random variables, looking at some observables phi, computed on the iterated dynamics. So in the IID case for random variables, you know that 2 main characterizations for that is the law of large numbers and the central limit theorems, which are quite important if you want to do a probabilistic description of the system. So if we continue to do this parallelism, we see that if we look at the invariant measures, which are measures which preserve the set under the dynamics, we can say that somehow this sequence is of identically distributed random variables. And the law of large numbers in this case reads like if you have this set, which is the set of points for which the time averages converge to the spatial average with respect to the invariant measure mu. This set is called the ergodic basin. And if this set has a positive Lebesgue measure, then we reasonably call it a physical measure, that we can actually see it. And this is already a challenge to find these kind of measures for given systems. And the next step should be to to have some independence of the observables. Of course, we cannot expect something like in the IID case, in the classical one, but at least we could hope for a sort of weak independence of the observables. And in this case, we say that the system is mixing. And for a long time, we see that the observables this limit gives the product of the observables with respect to the average with respect to the invariant measure mu. And in many cases, the mixing alone is not enough to prove to have some information on the system. And we would like to say something about the speed on which this limit occurs. And in this case, we talk about in the desirable case, we have an exponential decay of correlation. So we compute these correlation functions, and we would like to know how it goes to 0 as n goes to infinity. So these kind of questions may be addressed using this transfer operator method or the functional approach. If you had the chance to listen to Vivian Baladi's talk, you already meet this operator from L1 to L1. And this is just the composition with backward dynamics weighted with the Jacobian of the map. So the main characterization of this operator is that the fixed point of L corresponds to the invariant density of the systems. And so we can translate our problem to study the statistical properties of L. And in particular, we look at the invariant, we look at the eigenvectors associated to the eigenvalue 1, which corresponds to the invariant measures of the systems. So, having good spectral properties means that we have this ideal picture because unfortunately, if we look at the spectrum of L in L1, we get the full unit disk, which is poor information if we want to say something about the system. So this is what we would like to have instead, that L to find some Banach space inside L1 on which F behaves almost like a matrix. Meaning that the spectral picture is just like this, and we have single isolated eigenvalues up to a small part, which is this disk strictly small with the radius called the essential radius, strictly smaller than 1, and we call this part the essential spectrum. In this situation, we say that L is quasi-compact, because you see that if the essential spectrum is small, if it's at 0, you have a compact operator. So from the abstract functional analysis, we have this theorem. This is one possibility to prove that an operator is quasi-compact. And basically, without entering into the details, we would like to say that L acts almost like a contraction. Here, sigma is smaller than 1, up to some compact term, which comes from this other norm, which is a norm given in the weaker space. And this is compact because we also need this ingredient that the strong space embed compactly in the weaker space. Under this called the Lasota-York inequality and this other ingredient here, we can say that L is quasi-compact, and we have a bound for the essential spectral radius. So this kind of system, the uniform hyperbolic system in compact space, have been extensively studied in the last years, and we know a lot about these systems. And starting from the simplest case of a smooth expanding map in which you have that the derivative is greater than 1. In this case, the good space are the smooth functions. So you take a smooth functions and you apply the operator. As I said before, the operator is just, you can think about the composition with the inverse, with the backwards dynamics. And since the dynamic here is expanding, you can expect this contraction in the space. On the other hand, if you are looking at a contracting map, you cannot expect the same using smooth function because you're going on the other directions. So the idea here turns out to be to use the dual of the smooth functions, which are the distributions here. And in the uniformly hyperbolic case, in which you have the presence of contracting and expanding directions, the idea is to use the Banach space, which have a sort of anisotropy. And the basic idea is that when you move along expanding direction, you use smooth functions, while when you move along contracting directions, you use the dual. And you combine these two approach together to get what you need. This is the very rough idea. So these gentlemen and the ladies are the pioneers of this approach. Here for the smooth uniformly hyperbolic case, but as Viviane told us last time, also it works also very well for piecewise, for example, piecewise smooth hyperbolic. But we basically were interested into a non-uniform hyperbolic case, in particular in a partially hyperbolic case, in which you have also central directions in which you may expand or contract, but they are dominated by what happens in the hyperbolic directions. So here basically you are saying that along these directions the Lyapunov exponent may contract or may be positive or negative or even vanish. One example, which is deceptively simple example, is the skew product, in which you have a smooth map on the two torus, and you have on the first coordinate an expanding map here, and on the second coordinate the identity plus this omega, which is the fiber. And these kind of examples were well studied in the last years, and under some generic condition on omega, you can prove with the spectral method, you can prove all the good statistical properties that you need. The partially hyperbolic systems were studied by a bunch of people, and I'm sure I'm forgetting someone. But initially, we were interested in the study of this particular case, which is the fast-slow systems. And it's made by a family of maps parameterized by a small parameter epsilon here. And is a more complicated version of the skew product system, but is not a skew product. And the base map is an expanding map only on the horizontal direction. And the second coordinate with the slow variable is a perturbation of the identity. And in this case, for epsilon small enough, this is a partial hyperbolic system. And you have that the central Lyapunov exponent, so the Lyapunov exponent computed along the central direction, can be slightly positive or slightly negative or even zero. And in this case, we are saying that we are almost in the central direction is almost neutral, in which you have zero central Lyapunov exponent. This system has been studied basically by De Simone and Liverani in the last years. But in all of this paper, they either assume that the physical measures exist, or they have some condition that allows you to say that you are in the mostly contracting case, for example, here, and you take that the central Lyapunov exponent is almost everywhere negative. We would like to say some more, to have some more information and approach directly with the transfer operator. And we did it applying the transfer operator to a more general system that I roughly described here. So you have a local diffeomorphism on the two torus, which is partially expanding because we are in 2 dimensions. So you have one direction which is expanding, and the other direction, which is the central one, is almost neutral. So F epsilon is a subcase of this more general case. And under a checkable generic condition, unfortunately I cannot say some technical details on this condition, but fortunately in this case, Masato Tsuji proved that this condition is generic in this particular surface case. And we have also, in principle, a checkable way to see if this condition holds or not, maybe using some computer-assisted technology for a given system. And under this generic condition, we prove that there exist these Banach spaces, and they are contained in the standard Sobolev spaces HS. So we know that, for these spaces, we have quasi-compactness. And the good news is that I already said that the system in this case has finitely many physical measures, but we know that the densities are in HS, so this is slightly more information. And the mixing ones, if you look at the mixing ones among these physical measures, they enjoy exponential decay of correlation. So with this method, we have almost for free all of these informations for the systems. Yes, I almost done. As a corollary, we can say as a corollary, if epsilon is small enough, we can apply this the previous result to F epsilon, and we prove that this family of transfer operator are quasi-compact on HS, and the essential spectral radius is uniform in epsilon. Although, as long as you take epsilon goes to 0, you have more and more eigenvalues, but the spectrum is uniformly the essential spectral radius is uniform in epsilon. So I would love to say something more about this, but my time's up. So thank you very much for your attention.
Thank you very much. Are there any questions?
Okay, thank you. Hi.
Yes.
Oh, I'm not sure. Okay, so for the essential spectral radius,
yes.
Can you get some explicit dependence on epsilon, or?
Well, as I said,
I mean, like an explicit formula. I understand that you have some. No, okay.
No, we don't have an. We don't have an explicit formula for the essential spectral radius, but we do have the explicit bound in terms of
You have the
epsilon.
explicit bound,
Yes.
okay.
And in fact, is another result that if you ask for less regularity, for example, you take S equal to 1, we make a lot of effort to try to control the constants inside the Lazoda-York inequality to get some more information on the bound on epsilon. This is very important. We're still far away from an optimal bound because we didn't get the bound that we needed to have some more information nearby the peripheral spectrum, because when you have some more explicit formula for the essential spectral radius, maybe you can say something more about perturbing the spectrum. But yes, this we can did it because we have less regularity. And you can make more explicit computation in the formulas.
Okay, so thank you very much. Let's move on and thank our speaker again.
Thank you.
So oops, what happened? Okay, well, I can't see. No, I know, but okay. So, okay, our next speaker is Tanya Schindler, and she will speak about almost sure asymptotic behavior for infinite measure-preserving dynamical systems.
Okay, thanks for the introduction. Can you hear me like that? I think I have to get closer to me. Yeah, this is joint work with Claudio Bonanno, and well, the preprint is already online since a couple of months. And just to give an introduction, oh, sorry. Well, I will just give an introduction and then say something about L1 functions, and then if I have enough time, also something about functions not in L1. And well, we first have to start giving the setting. So we will always consider a conservative ergodic measure preserving transformation and a sigma finite measure space. And for simplicity, we assume that our observable is non-negative and, of course, measurable. And then we define the Birkhoff sum in the usual way, like the sum of the observable composed with the transformations. And now what can we say about pointwise convergence of this Birkhoff sum? And well, very classical theorem in ergodic theory is Birkhoff's ergodic theorem, of course, and then we get, okay, if we are in a probability measure space, then, well, we get the strong law of large numbers. However, from now on, from the rest of the talk, we assume that our measure is infinite. And then we get also by a very classical theorem by John Aronson that things are more complicated. So if our function is in L1, and no matter which norming constants, I stop with that, Bn we chose, then no matter, then either we infinitely often almost surely overestimate, or we infinitely often almost surely underestimate the sum. So well, we don't really get something like a strong law of large numbers. However, if we look at a function which is not in L1, then well, there can be examples such that we get a strong law of large numbers. And well, I mean, if you do a very stupid example, you can just choose f to be constant. But we want to look at more advanced examples. And well, to my knowledge, there's only a paper by Marco Lenzi and Serramandi, who have studied this behavior in detail. But if anybody knows more, then please let me know. But now we come to the main questions, which I try to motivate now. So if F is in L1, can we somehow truncate this Birkhoff sum Sn such that we get this, this strong law of large numbers, so that we truncate this sum and then we have a norming sequence such that we get an almost sure convergence. And the second question is, okay, we assume F is not in L1, and how does it have to look like? How does the system have to look like that we get a strong law of large numbers, like almost sure convergence? But now back to the L1 case, and I will first introduce some notation so I can also state the theorem. And so we first denote, we consider some measurable set with measure 1, and we look at the first return time. That is the time it takes that if you start with some point x and iterate it, that you end up in E again. And well, by classical considerations, one knows that the first return time is finite, almost surely. And so we can introduce the induced map. This means it's a map from E into itself, and you basically map E, and you start in E and go along the orbit until you are in E again. And then we also introduce the superlevel sets. Those are all these points for which the first return time is larger than n. And then we denote the longest excursion out of E beginning at the first n steps. And well, the formula is given there, but it's maybe a little bit hard to digest at the first moment. So what are we actually doing? So we go, we sample along n. The red dots mean those points which are in E. And now, okay, we are not in E at the moment, so we look at the next point in E. We are in E, and then we look, okay, where is the largest excursion? And here it is happening at the last point, which are actually after n, but it does not actually have to happen. It could also be something like this. And now with that, I can state the theorem. So again, we are in this setting as before. We have infinite sigma finite measure and this set E. And then we have some assumption on E. So we first assume that this sequence phi E composed to T E to the n-1 is a psi mixing sequence. And well, I don't want to explain psi mixing here, because if you haven't seen it, it's a bit of a lengthy definition. It is actually a little bit stronger than this decay of correlation we have seen before in Roberto's talk, and you can, well, in terms of probability theory, you can assume it at like observables far apart from each other almost behave like independent random variables. And then we have another condition on the superlevel sets. And then we, with these two conditions, we actually get this strong law of large numbers we were interested in. And so what are we doing? So instead of looking at the actual Birkhoff sum, we look at the truncated Birkhoff sum. And we truncate it in that way that we add additional summons. And the additional summons we were looking at are just these And this M we were looking at before, like this longest excursion out of E. So that many summands we have to add. And then we have a norming sequence which is not N, but we can actually directly calculate the norming sequence. And so just an easy example, I don't want to give too many details because it's delayed. So we can consider, for example, the Theorem map, which is given here, and this is a map which has an infinite sigma finite measure. And we can look at an observable F, which is given here, which is piecewise constant. And this piecewise constant, for instance, assures that the thing is psi mixing. And well, instead of the Theorem map, you can also use the Pomo-Menville web or Livarani's or Solvay-NT maps, or actually you could also fiddle around a little bit with the parameter, so that excursion could also be regularly varying with exponent -1. And I think I have 1 minute or so. Oh, okay. So then I can say something about the second theorem. And here I will actually not explain the complete theorem. So this now is the second question. We would like to look on some convergence criteria such that for f not in L1 as an f over Bn converges to 1 almost surely. And here I will only give you the theorem divided by n. I mean, in the preprint you can have the full version, but then I have to state just a very long list of technical conditions, and I thought it will not be so easy to understand in an evening talk. And so it's just the conditions. I actually thought I will run out of time, so I put them all on one slide, but then as I have maybe not a minute, I can say a little bit about it. So the conditions are actually quite similar to the first theorem. So we again have this mixing condition as in theorem 1, and we also believe this is a kind of a necessary condition. And we also have this condition on the super level sets. And then we additionally have that f has to be constant on the level sets. Well, in the last example we already had this, but here we actually have this as a condition. And then additionally to this condition 2D, I just labeled the conditions as in the preprint, so in case you look it up, they are the same. Additionally to the conditions on the super level sets, we have to restrict it even more. And under these conditions, you just get this strong law of large numbers. And with this, I finish, and this are the sources I used, and I'd like to thank everybody for their attention.
Thank you very much. Are there any questions? Yes, please.
Is the class of sequences Bn that you obtain exhaustive? I mean, you found the existence of some scaling sequence Bn for which you have some almost sure convergence. Is that class of sequences exhaustive, or you say there exists a scaling, but to me it wasn't clear if that's the whole class of sequences for which you get the almost sure statement or not.
I mean, it's quite clear that that not all of the conditions are really necessary. Some of them are kind of. I mean, there is this, for example, this mixing condition, and I don't think you can very much weaken it. But you were explicitly asking, okay, if I understand it correctly, I mean, here I only divide, you were referring to this theorem or to the other one?
I think it's, no, the one with the Bn, but in any case, probably.
This one, right?
Yes.
And you were referring to the norming,
yes.
The norming sequence.
Yes.
There is there is very small potential for more, but not for much more. There are certain reasons why it can't be that easily generalized. There are possibilities that instead of that you only add this m, you might add even more. And then you can have a larger class of norming sequences.
I'm especially asking this question because there is a follow-up work on the work we mentioned of Aronson, which is long ago. So they have almost sure statements for the lim sup and lim inf. And this is also, so in that sense, it looks like there is some room. I'm not sure.
Yeah, I think I know this work, and I think like then, I mean, they have actually broader classes of random variables. And I think, I mean, I'm pretty sure that there are examples in this paper of distributions where this thing will break down.
Thanks.
Okay, so thank you very much.
Okay, so our next speaker is Caroline Wormell, and the title is Emergence and Breakdown of Linear Response in Globally Coupled Systems.
Thanks. So yeah, this is joint work with Gail Gottwald from the University of Sydney. And so as the title says, it is, hang on. How do we make it work? Hey, there we go. All right, so yes, this is a talk about linear response. So the setting for this is that you have some family of chaotic systems, and we're going to say they're discrete time, and they're parameterized by some, there we go, some parameter epsilon, which is, you know, say a real number, and each of these systems is, you know, they're nice, they're mixing, they have decayed correlations, and they have some, each have some physical measure, rho epsilon. So you've heard about physical measures. The idea of them is that they encode the kind of long-term ergodic behavior for generic initial conditions, and in particular, if you have some Birkhoff sum, it will converge to an expectation with respect to the measure. And now, of course, because the dynamics depend on it, like the map depends on epsilon, the physical measures depend on epsilon, and so these expectations will also depend on epsilon. And if you change the system a bit, your expectations will change. And you can think of many examples where that might happen. And the idea of linear response theory is to say, well, okay, how do these expectations change as we change this parameter? And in particular, because, you know, we love derivatives, we love calculus, what is this derivative? How can we compute this? And of course, there are ways we can compute this. There are plenty of ways to do this, and there are plenty of ways to use this in terms of sort of approximations. But there is a fundamental assumption underlying this, which is that this expectation is, in fact, as a function of epsilon, is differentiable. Being chaos, this is not necessarily the case, but we have some theory, and we know that in certain circumstances it does work. So, for example, in statistical mechanics, we've known for ages that it works. For stochastic systems that, you know, have some kind of reasonably nice regularizing noise, we know it works. For ICMP systems, so that is like uniformly hyperbolic systems, we have Ruel showed 20 years ago that it works. But for other distributive systems, it's a little bit harder because, well, it's a lot harder because it's hard to prove anything about these things. But if we look at the simplest kind of non-hyperbolic system, that is the logistic map or quadratic maps more generally, it has been shown that even if you look at sort of, you ignore all these horrible, like, periodic windows, say, if you're familiar with these things, even if we just look at a sort of small subset of parameters that are quite nice, we don't get a linear response. We get some kind of we get a Holder response. This expectation function is only Holder, and we can't do any better than that. So that kind of throws into doubt whether we can even use linear response theory for non-hyperbolic systems, which are, almost all the ones we see in real life. Nonetheless, geophysicists have gone ahead and just had a go, and generally they've been very successful. So there's, they've looking at really simple models, but they've also looked at like very serious, like global climate models, and gotten some good results. And the kind of rationale for this is the so-called chaotic hypothesis of Gallivardian cone, which is that, well, if we look at the kind of large-scale dynamics of these, big climate systems, really they're like ICMP systems, which, as we know, have linear response. However, there are some systems where it doesn't work. So, for example, this is an El Nino kind of model, and you get this kind of quite rough response that you probably wouldn't want to take a derivative of. So given that it seems to work in a lot of systems, although we don't know why, really, and sometimes it doesn't work, this motivates kind of the talk, which is going to be asking the question, basically, when does linear response happen or not happen, and why? In these kinds of dissipative systems that are, have a lot of dimensions to them, and in particular, whether it works at this macroscopic level, which is, perhaps the most physically important one. And of course, that's a very broad question, so we're going to look at a nice sort of model of like, a complex system that we can deal with, which is specifically if we take a bunch of coupled maps, which we have a bunch of chaotic maps, which we couple via a mean field, and we're going to look at really two cases. Firstly, when we take the number of maps to infinity, so this is the thermodynamic limit, but also then, because we want to sort of be a bit more realistic, to look at when m is finite, but I guess fairly large. Oh no, don't do that. How do I stop the monitor from turning off? Is that a real thing? It's telling me it's going to turn off. Okay, we've got 20 seconds to figure that out. So the model actually sort of concretely looks like this. So we have a bunch of microscopic systems Qj, which are all evolving according to some microscopic dynamics little f, which obviously depend on this parameter epsilon, and also on a mean field, which is just an average of some observable, it turned off, some observable over, on the Qj. So it's a mean field. And we're going to observe this mean field just to keep things simple because it's a macroscopic variable. And this has been studied for like 30 years, since at least Kaneko's work. And they have some really quite rich behavior. Okay, so we want to reduce this model a bit. And the way that we're going to do that is we're going to use the kind of exchangeability of these QJs, because they all have the same behavior, to look at the empirical measure of these, their empirical measures. So basically, take a sort of bunch of delta functions. So we're working, instead of like, this m-dimensional system, we're going to work on a set of measures, a space of measures, and we get the system as just a push forward under the microscopic dynamics of this measure. So this is kind of like a transfer operator, this f epsilon star, and I'm sorry that my pointer's dodgy because I'm here. But then also, this push forward is being modulated by this mean field, which is just an average over the measure. So, as we take m to infinity, we expect that this empirical measure is going to sort of turn into some nicer measure, which is, we'll say is like, it seems very reasonable to assume that this is a physical measure of this co-cycle that we're pushing forward our measure by. And so in particular, this co-cycle, it depends on epsilon, our parameter, but it also depends on the history of the mean field. And what this means then, if we think about the mean field is just an average over the measure, so we actually can write the measure in terms of its, so the mean field in terms of it as a function of its history. So we have this very nice closure, right? We've gotten rid of all the microscopic dynamics, at least explicitly. But now, of course, we need to think about, if you want to think about linear response, the next thing we need to think about is, well, what are the dynamics of this? Now, one thing is that if the microscopic dynamics are mixing sufficiently, then the past history of phi n, like the deep past, like phi n minus 1,000, isn't going to matter because it's all going to have washed out. So we can kind of truncate this f at some point. It's quite good accuracy, and what on some level this means is that we have effectively at least very close to low-dimensional dynamics. So yes, the macroscopic dynamics in this thermodynamic limit are deterministic, and they're very close to finite dimensional. And furthermore, kind of conversely, if we're just given some deterministic finite dimensional map, what we need to do, we can actually like cook up a coupled system, one of these coupled systems that actually approximates the dynamics of this map we chose. So kind of what we know is we have finite dimensional systems where really we could see anything. And so more concretely, we chose some microscope, like simulated one of these systems with like some uniformly expanding microscopic dynamics. So everything's really beautiful. It's good. We expect our capital F to be smooth, which we can't always guarantee. And okay, so we cranked our parameter epsilon up really big, and we found, well, okay, we had a sort of nice kind of, periodic behavior here. This is beautiful, probably has linear response. But we got a period doubling cascade in this system that we cooked up that eventually goes to chaos. And it's kind of logistic, like Henon-like chaos, at least if you look at it, you look at the bifurcation plot here. But if we looked at the linear response, like the logistic map, we see a failure of linear. Like this is not a nice, you can't differentiate a lot of this. And in fact, we can go a little bit further. We sort of looked at the geometry of this system, and we found homoclinic tangencies in the dynamics of this mean field, which actually means that the dynamics of this mean field are non-hyperbolic, which is at some level a contradiction, is really opposite to what the chaotic hypothesis that geophysicists like to use says. So the world is not perhaps as beautiful as we would like it to be. In this thermodynamic limit, at least. Of course, certainly like in climate science, we don't have a very nice, there's not a lot of nice scale separation that you would need for the thermodynamic limit to be really valid. So we might at least want to consider a sort of first order correction to this. So in this case, we're going to assume that we have a large but finite number of particles here. And okay, if it's large enough, it's reasonable to assume that these particles are all sampled from this physical measure that we get from the, this time-varying physical measure that we get from the from the thermodynamic limit. So obviously when we sum phi n, which is again is like an average of some observables of the microscopic dynamics, there we go. We get the expectation, which is just the average over the physical measure, plus a central limit theorem correction term, which actually, if we sort of think about it as a process in time, it's a mean zero Gaussian process, and we can compute its covariance, and in particular, it will have a decay of correlations. So the upshot of it is that this dynamical system that we get out for this finite M is a stochastic dynamical system that's, it's a very nice stochastic dynamical system, and because we know that stochastic dynamical systems have linear response, we expect to have linear response of these phis, of this mean field, which integrably comes out of the finite size effect because we've got this noise. And obviously, as the noise is smaller, the sort of linear response properties are going to get worse. And in fact, that's exactly what we see. We see here, so we see that, like in this system here where we have a bunch of unimodal maps, so logistic maps all coupled together, we get linear response for like reasonably large, but not too large M. We sort of get this horrible bifurcation behavior. But actually, this in itself is kind of surprising because if we if we didn't have any noise, this would actually be a horrible, horrible function. It'd be something like Holder because the smoothness of this depends on the linear response properties of the microscopic system, which are bad because they're logistic maps. But somehow the noise actually really magically makes everything beautiful and lovely, and we get linear response in this finite dimensional system, like kind of more than we would even expect by the arguments on this slide. And furthermore, this actually works for really quite small ensemble sizes. So here we pick, M equals 3, we get this nasty little thing here, but for like, where we have like 4 of these subsystems, we get quite a nice, sort of perhaps differentiable system. And at this sort of level size of system, this dimensionality, there's probably some there is definitely some connection to some work by Ruel, which I'm sort of trying to follow up, on the distribution of singularities in these physical measures, which is really, I mean, from Baladi's work, say, is what is thought to cause a failure of linear response in these non-hyperbolic systems. So there's, I guess, a nice connection between the sort of large dimension and the small dimension theory there. But to sum up, we've sort of, in this talk, we've sort of discovered, or been studying these globally coupled systems that are coupled via mean fields, really as a model for like high-dimensional chaos. And well, we find that at finite size, basically we have this emergent stochastic effect coming from a kind of central limit theorem, which makes everything nice. It means that we get linear response. Beautiful. In the thermodynamic limit, however, this noise disappears and we have a lot more conditions to get linear response. We need that the microscopic dynamics satisfy linear response themselves, which I probably didn't talk about too much, but it's the case. And we also need that the macroscopic dynamics are nice, that they themselves like kind of, are the kind of systems that have linear response. They're hyperbolic or they're periodic or something like that. But this isn't always the case. We have seen that this is not always the case, which is actually kind of surprising in itself because it has been hypothesized that it is. There are actually other ways in which sort of making us, as well as having finite size, there are other ways in which making our system look more realistic. For example, if our subsystems are all a little bit different, this can help us get linear response in the macroscopic scale. So I guess there's a natural question, which is how do we, because obviously globally coupled systems are not, could be more realistic. We could think about, well, what happens if we have other kinds of coupled networks? Which maybe, it's an interesting question as to what would happen in that situation. But if you want to read more about this, it's in this paper here, and hopefully this paper here, which will be in about the homoclinic tangency, will be on the archive in a couple of months, I think. So, thank you.
Okay, thank you very much. Are there any questions? Yes, please.
Just wanted to know, you claim that you have this example in which the hyperbolic hypothesis does not hold, right? But you know if this example is inside some subset that you can somehow avoid, or you may expect that in generic case you have the hyperbolic,
So there's okay, so this is something that I'm trying to prove things about, but we know that generally when you have a hyperbolic, like these kind of homoclinic tangencies, you will find a neighborhood also other homoclinic tangencies, which also obviously mean that your system is non-hyperbolic. And in fact, furthermore, we can say because we can really find kind of any kind of dynamics with this map, like in that second bullet point, perhaps with G we can construct a system that has a blender in it, and then we know that we have kind of robust non-hyperbolic dynamics. So and there would be, robust to any kind of perturbations we want. So on some level, yes, this is generic. Whether, like hyperbolic systems, whether it's something that we'll actually see in most realistic systems is another question, but I think it's an interesting.
Thanks.
Because I think I didn't understand something. At a certain point, we were discussing the field situation, and then you said that there was some truncation, but I couldn't understand exactly what was depending from the history. But the mean field does not really depend from the history. It's a market process. You can maybe give the mean field, but sorry, I didn't understand something over there.
Okay. So I suppose there's two ways you can really think about this limit. Yes. So at one level, you can think about it as the mean field gives you, the measure gives you the mean field, which gives you the backer measure by the push forward. Yes. So that's Michael. Yes. But you could also think about it as, well, the history of the mean field gives you the measure, which gives you the mean field back. So I think they're two equivalent ways to do it. We found the homoclinic tangency in this measure, yes, but I guess I wanted to Keep it simple, yeah.
So thank you very much again.
Please, for the streaming, speak in the microphone and turn them on when you answer the questions, please.
Right, exactly. Did you hear that? Okay. All right, so our next speaker is Reza Mohammadpour, and he will speak about Lyapunov spectrum properties.
Thank you very much. Thank you very much for the introduction. I'm so glad to be here. Oh, okay. Okay, let me mention the general setting of this talk. This is the compact metric space that's endowed with metric D. XT is a topological dynamical system, and MXT, the space of the all-T invariant Borel probability measure, which is convex and compact with respect to weak star topology. And EXT, the subset of the ergodic measure, which is the extreme set of the space of the T invariant Borel probability measure. Let f be the continuous function. I will skip the definition of the Berkoff sum and Birkhoff average as the Tanya explained. So by Birkhoff ergodic theorem, we know that Birkhoff average exists for almost every point. So one may ask about of the minimum or maximum value of the Birkhoff averages. We denote by alpha L the limit of the 1 over n infimum of the Birkhoff sum over the compact metric space X, and beta f the lim 1 over n the supremum of the Birkhoff sum over the compact metric space X. By faculty lemma, the limit exists, and by compactness, one can show that the beta f is the maximum value of the Birkhoff averages, and the alpha f is the minimal value of the Birkhoff averages. And the alpha f and beta f are called the minimal and the maximal ergodic averages. And it's easy to see that alpha f is equal to minus beta minus f. Just put the minus in the definition. So we can just focus into the quantity of the beta, which can be characterized as follows. Supremum of the integral f d mu over the space of the T invariant Borel probability measure. Since the space of the T invariant Borel probability measure is a compact and convex with respect to weak star topology, supremum at n and such a measure will be called the Birkhoff maximizing measure, as I explained here. And we denote the set of the measure which the integral of f d mu equal to maximal Birkhoff averages by m max f. We know that this set is the non-empty. In fact, it's the compact and convex with respect to weak star topology. Assume that the phi n is a continuous positive value function on the compact metric space X. We say that capital phi, which is the set of the log phi n, is a subadditive potential if phi n m plus x is smaller or equal than phi n x, Vm Tn x for all x and Mn. Is almost additive potential if there exists C greater or equal 1 for all x and Mn, C minus phi n x, Vm Tn x is smaller or equal than phi n plus x, is smaller or equal than C, phi n x and Vm Tn x. And additive potential if phi n plus x equal to phi n x, Vm Tn x for all x and Mn belong to natural number. Birkhoff sum is an example of the additive potential because you can define it phi n x equal to e power the Birkhoff sum. So let us see the example of the subadditive potential. Matrix co-cycler example of the subadditive potential, to be more precise, given a continuous function of the A from compact matrix X to a space of the invertible matrices, we consider the product of the A and X, which is A, Tn minus X till Ax. The pair of the Ta is called the linear cocycle. Linear cocycle can be written as a skew product such that Xv goes to Tnx, Anxv. And if T is the invertible, so is F. And you see the formula for the F minus Nx, which is equal to T minus X, A minus X. And the formula for the inverse A power minus X, you see the formula. As I say that matrix co-cycle is the example of the subadditive potential, so let me show why. By Q-Mang subadditive theorem, we know that for any mu belongs to a space of the T invariant Borel probability measure mu almost every x, such that the positive part of the logarithm of the norm A is integrable, the top Lyapunov exponent at x exists. More precisely, xA is equal to lim 1 over n log norm of the AX. Norm is the operator norm or first singular value, and by property of the norm, norm of the AN plus x is smaller equal than norm AM Tn x times norm AN x for all x and Mn. So as you see, that matrix co-cycle is an example of the subadditive potential. We can also define the Lyapunov exponent measure, which is integral of the top Lyapunov exponent, and if the measure is ergodic, the top Lyapunov exponent is equal to Lyapunov exponent measure. Similarly to what we did for Birkhoff averages, one can minimize or maximize top Lyapunov exponent. So we repeat the story as I mentioned at the beginning. To be more precise, the maximal Lyapunov exponent is equal to lim 1 over n log supremum of the norm AN x over the compact metric space X. Again, the limit exists by Facketel lemma, and that's equal to supremum of the Lyapunov exponent measure over the space of the T invariant Borel probability measure. Since the Lyapunov exponent measure is upper semi-continuous and the space of the T invariant Borel probability measure is a compact and convex, supremum is attained, and such a measure will be called Lyapunov maximizing measure. And we have the same story for minimal Lyapunov exponent, which is lim infimum of the 1 over n log infimum of the norm ANX over x, and that's equal to infimum of the Lyapunov exponent measure over the space of the T invariant Borel probability measure. But this infimum doesn't necessarily attain. It means that one can give an example such that there does not exist an invariant measure such that the Lyapunov exponent measure equal to minimal Lyapunov exponent, as I explained here. Now I'm going to work the following co-cycle. T is a topological mixing subshift finite type, and the A is a Holder continuous. Fix theta between 0, 1 and endode sigma with the metric D such that for any 2 points of the X and Y belong to the symbolic space of the C, distance defined theta power K, where K is the largest integer such that Xi equal Yi for all lengths I, a smaller K. And equate with such a metric, the shift operator T becomes hyperbolic. And I also assume that T invariant measure on the sigma have a local product structure. For example, Gibbs measure has a local product structure. So I'm going to work with this co-cycle. I also assume that my co-cycle is a fiber bunch. What does mean fiber bunch? All Hordel continuous function A is a fiber bunch if for any x belong to symbolic space, norm AX times norm inverse x times theta r is smaller than 1, where theta is a hyperbolic city constant defining a metric. Fiber bunching, it means that your co-cycle is nearly conformal. What does mean nearly conformal? If you consider any conformal matrix satisfying the fiber bunching, if you perturb a bit your conformal matrices, again, they satisfying the fiber bunch assumption. That is why when your co-cycle is a fiber bunch, they say that it's nearly conformal. And we say that a linear co-cycle T is fiber bunch if its generator or A is a fiber bunch. And we denote by HBR sigma GLT the family of the all-Holder continuous and fiber bunch function. Bonatti, Gomez-Mon, and Viana, they show that Holder continuity and fiber bunch assumption imply that converges canonical stable and unstable holonomy. To be more precise, for any y belong to local stable and unstable, a stable holonomy from point x to y is a lim inverse of the n y and x when n goes to infinity. An unstable holonomy x to y is a lim inverse n y and x when n goes to minus infinity. Let me mention Kali and Sadiviskova extended their result for partial hyperbolic system. So there are stable and unstable holonomy. The linear co-cycle F, again, base map is the topological mixing subshift finite type, hyperbolic and invariant measure the local product structure, and the fiber is the fiber bunch co-cycle. is satisfying the pinching and the twisting condition if there exists a periodic point such that pinching condition, they say all eigenvalue of the AQPU have a distinct value, and twisting, they say there exists a homoclinic point Z of the P such that loop holonomy psi pz twists in the direction of the AQP, where the loop holonomy is the composition of the stable and unstable holonomy. Pinching condition is clear. You just said all eigenvalue have a distinct value. Is very difficult to work with this. But the twisting condition might not be very clear. So let me explain in the following picture. This picture is in dimension 2. P is a periodic point and Z is a homoclinic point. If you take any vector in the tangent space of the P by unstable holonomy goes to tangent space Z, and by a stable holonomy comes back. That's the definition of the loop holonomy. When you come back, never overlap with any eigenvector. This is the definition of the twisting. As you see, when it comes back, never overlap with any eigenvector in the tangent space at the P. W is a set of the co-cycle, which is the fiber bunch and the holder, and A is the pinching and the twisting. This set is open and the nest, and it was shown by Bonetti-Viana. In fact, they extended the Festenberg assumption. As I mentioned, the top Lyapunov exponent exists for almost everywhere. So one may ask about the size of the dose of the point where the top Lyapunov exponent exists and equal to alpha. And the size usually calculated in terms of the topological entropy in the sense of the Bowen, because a level set is not necessarily compact set. So level set is the set of the point where the top Lyapunov exponent exists and equal to alpha. And the Lyapunov spectrum is a set of the alpha such that there exists a point, the top Lyapunov exponent is equal to alpha. As you see, the Lyapunov spectrum and the level set their definition are similar to each other, and we would like to see that what's the relation between them. That's the second question. And omega is the set of the Lyapunov exponent measure where mu belongs to a space of the invariant Borel popularity measure. So first, let me give an answer to second question. I mean, relation between of the Lyapunov spectrum and level set. Let A belongs to the space of the generic co-cycle. Then the Lyapunov spectrum is equal to closure of the alpha, where the topological entropy of the level set is a positive. And the function of the topological entropy is concave inside of the interior of the Lyapunov spectrum. We have a following picture. Inside of the Lyapunov spectrum, topological entropy of the level set is a positive. In fact, there is a conjecture that says that topological entropy of the level set at the maximal Lyapunov exponent at this point is 0 under generic assumption. This conjecture is still open. In case of the Birkhoff averages 2 years ago, Gonzalo Contreras proved that this is 0 under generic assumption. But in case of the Lyapunov exponents, it is still open. Denote the phi A, the log norm A. Now I'm going to answer my first question. Size of the level set. Assume that T is a topological mixing substrate finite type, A is a generic co-cycle, then topological entropy of the level set is equal to supremum of the measured theoretical entropy, where the Lyapunov exponent is equal to alpha, and that's equal to infimum of the topological pressure minus alpha Q for all A belongs to Lyapunov spectrum. So that formula is called a restricted variational principle, because in the variational principle we restricted to alpha level set. And we have a picture something like that. So we can define of the Lyapunov exponent for any subadditive potential, and I wrote all definition here. Maximal Lyapunov exponent, the Lyapunov exponent measure. Let X T be the topological dynamical system such that the entropy map is upper semi-continuous and topological entropy is finite. Suppose that phi is the subadditive potential in the compact metric space X. Till here, since we assume that the entropy is upper semi-continuous, so there exists an equilibrium measure. And we know that the space of the equilibrium measure is a compact and convex with respect to weak star topology, so there exists convergence subsequent. But what I showed that at any weak accumulation point of the family of the equilibrium measure mu t for potential of the T phi, where T positive has a Lyapunov maximizing measure. It means that any accumulation point, Lyapunov exponent of the any accumulation point is equal to maximal Lyapunov exponent. Moreover, I showed that continuity of the Lyapunov exponent, where the mu ti goes to mu, we have a continuity of the Lyapunov exponent and the continuity of the entropy. I'm not talking about of the existence of the limit, because limit doesn't necessarily exist. I'm talking about of the accumulation point. And the last thing I'm going to talk about of the continuity of the minimal Lyapunov exponent. Let xt be topological mixing subsheet finite up. Suppose that A and AN, two sequences of the matrices over the topological mixing subsheet finite up, and the phi A has a bounded distortion property, just phi A. I also assume that there exists of the family of the invariant cone field. Then we have a continuity of the minimal Lyapunov exponent. And let me mention, you cannot remove of the assumption of the invariant cone field, because there is some contour example. And thank you very much for your attention.
Thank you. Are there any questions? Yes, please.
I wonder if your result is related somehow to the fact that the space of ergodic measures is pairwise connected for hyperbolic base.
I don't understand your question. Could you ask, because I couldn't hear.
So if you consider all the ergodic measures on a hyperbolic base, so in your case you have this mixing system, then this space is going to be piecewise connected. So you can just take any two measures and connect them by continuous arc inside of ergodic measures. So if you just move along that arc, if you use that continuity, then you probably can show some properties of the corresponding quantities that you analyze here. So I just wonder if there is any actual connection that you can see in your proof.
In case of the piecewise constant, it's much easier than after these cases, because I'm working with the Holder's things. In this case, no?
That's not what I'm asking. The space of ergodic measures is path connected. So you can connect any two ergodic measures by a path, which means that for any intermediate value, you will get the corresponding set that you analyze. So that's maybe you should talk later.
Yes.
Any other questions? If not, let's thank the speaker again.
So I think the next speaker is an online speaker.
Yes.
Okay. All right, great. Okay, so great. So our next speaker is Jason Atnip, and the title is Thermodynamic Formalism for Random Interval Maps with Holes.
Thank you. I can't seem to turn on my video, but that's fine. You don't need to see me. It's very late here. But thank you. And so let's get started. We're going to talk about random interval maps, and we're going to poke some holes. Okay, so first, let me say this is all joint work with Gary Froyland, Cecilia Gonzalez-Tuckman, and Sandro Baenti. Maybe let's start off with a simple deterministic example first. So the idea is, well, let's look at the unit interval and let's take the map. T of x is 3x mod 1. Okay, and I want to put a hole in our system, and let's just take the hole to be the interval from 1/3 to 2/3. So just delete the entire middle branch. So the Birkhoff ergodic theorem tells us that Lebesgue, almost every point, will eventually be mapped into the hole. So it will eventually escape. And so from this, two natural questions arise. We can ask, at what rate does the mass escape through the hole? And also we can ask, what is the kind of size of the surviving set, right? It has Lebesgue measure 0, but we can ask about the Hausdorff dimension. In this case, the surviving set is just the Cantor middle third set, which of course we know has Hausdorff dimension log 2 over log 3. And we can also show that this escape rate has to be log 3 minus log 2. Now, the idea here is to generalize the work of Livrani and Maume-Deschamps, and we want to look at these kind of open interval maps, but in the random setting. So what I mean by that is we'll start off with a probability space, omega, and an invertible ergodic map, sigma, which preserves our probability measure m on the base. And now for each omega, I want to look at a surjective interval map, T omega, from the unit interval onto itself, such that there exists a finite partition, Z omega, of our interval, such that, well, for each Z, T omega of Z is an interval, and T omega restricted to Z is continuous and strictly monotone. We'll iterate our maps by, say, T omega n. Well, that's just going to be T sigma n minus 1 omega composed all the way down to T omega, where we're just iterating along the sigma orbit. Okay. Now, our main tool will be the transfer operator. So I should define my closed transfer operator. And to do that, we first start off with our Berkoff sum, which here we're taking, say, some function f, and we're creating our Birkhoff sum along the sigma orbit. So where we're summing up f composed with T omega j for increasing j's. And now we'll consider a general potential, say phi omega c, just to be a BV potential. And we'll define our weight function g omega n, just to be the exp of Sn phi c for every omega. And then finally, we can define our closed transfer operator. All of these objects have a little c to note that these are on the closed system without holes. But our closed transfer operator will be the usual sum along the pre-images of the weight function g times our function f. Okay. Now, before we talk about open systems, let's first talk about our closed systems. We need to assume that our closed system, there exists a closed conformal probability measure on our closed system, and that means there's some, say, random measure nu, which satisfies this equivariance condition. And we'll also assume that these kind of random eigenvalues, lambda omega, that these are log integrable. Now, with the same group, Gary, Cecilia, and Sandro, we proved that such measures exist for large classes of random interval maps, which we called random weighted covering systems. And now, to talk about open systems, well, for each omega, we're going to let h omega be some subset of our interval, which has positive closed conformal measure. And from there, we can define, just like we would defining our Cantor set, we can define the nth level survivor set to be the set of all points whose trajectory does not land inside of any hole for at least n steps. Okay. Naturally, we define then the true survivor set, x omega infinity, to just be the intersection of all these x omega n's. Finally, we get to our open transfer operator, which we just pre-compose our closed transfer operator with the indicator function on the complement of the hole. And all this does is it kills off any points on the hole before we push forward. Okay. Now, before we keep going, let's talk about an example. So for this, we can look at a class of random beta transformations. And by that, I mean, say for each omega, pick a beta omega, and then we'll look at the map T omega x equal to beta omega x mod 1, where we can take a geometric potential that looks like just minus T log beta omega. Now, this assumption up here at the top just is saying that none of our beta omegas are too close to an interval, kind of uniform in omega, which gives us kind of a nice covering condition. And we also need some appropriate amount of expansion, assuming that the, on average, log floor of our beta omegas is, say, bigger than log 3. Now, if we assume this, these assumptions assure that the closed system behaves nicely. And as for the open system, we need no further assumptions. And if we assume the whole is, say, the final branch, the interval containing 1. So maybe a picture is a better way to express this. I just want to pick that whole to be that final branch for our map. Okay. Now, if you don't like these examples, well, first of all, we could move the whole around, or our whole doesn't have to be in a single interval at all. It could be just any finite collection of intervals. But we could also talk about random non-uniformly expanding maps, a large class of random Lasota-York maps, or even random non-covering maps. Okay, our results can cover all of those. Now, to properly define our assumptions, I need to first talk about some refinements of our monotonicity partitions. So I'm going to let these Z omega n's just be the refinement of pullbacks of our Z omega 1s from future fibers. And from there, I will look at subcollections, and let's define this Z omega n star, which will just be all of our intervals in Z omega n, which are contained in the n-1 level survivor set. And of those, we can look at this Z omega f collection, which is just going to be all the intervals in Z omega star, which are full branches. And Z omega u will be all the ones that are not full branches. Finally, we'll say that two elements of Z omega star are contiguous if either they are contiguous in the usual sense, in that they share a common boundary point, or if they are separated by a connected component of the pullback of the whole. Okay. Now, from there, I can state our simplified main assumptions. Our true main assumptions are quite a bit too technical for a 10 to 15 minute talk. But if we simplify this down and just look at full branches and non-full branches, we can give something simple. So first, let me say that let's let zeta omega n be the maximum number of contiguous non-full intervals. And from here, our three assumptions will be that, well, first of all, we have at least one full branch. Second, let's say that the number of connected components for our whole is log integrable. And finally, we satisfy this Q1 prime condition here. This is a kind of open contracting potential assumption in the spirit of, say, Liverani-Sasson-Vaillanti or Liverani and Maume-Deschamps, which is basically just saying that the exponential growth of our bad non-full intervals is growing slower than the kind of contraction rate. Now, with what we have, we want to use the Birkhoff cone technique that was kind of perfected by Liverani and then used by Liverani, Sasson-Vaillanti, and Liverani and Maume-Deschamps. And we want to use that cone technique to find a unique invariant density and a unique conformal measure. I'm not going to get to all the setup of that, but the main result we get from that is we're able to prove this cone contraction lemma, where we are contracting in the cone C omega plus, which is just all the positive BV functions. And here theta omega plus is the Hilbert metric on our C omega plus cone. Now, the main takeaway of this lemma is that we're able to prove that our kind of normalized transfer operator, if we go backwards in steps and then push forward in steps, so we're always in the C omega fiber cone, that sequence is Cauchy, meaning we'll eventually converge to an invariant density on the omega fiber. Okay, slightly kind of out of place here. First is that, well, we actually want to have some sort of conformal measure. So what we might usually do is try to use, say, a fixed point theorem, like the Schauder-Tikhonov fixed point theorem, to obtain a conformal measure. Here in the random setting, that doesn't quite work. And so we again follow Livrani and Mom Deschamps by defining this capital lambda functional on VV as this limit of this infimum of ratio of transfer operators. Now, the takeaway here is just to look at that capital lambda definition. And the point is that it's almost a measure. It satisfies a lot of properties of measures, but it's not quite there. Okay. And now using that cone contraction, like I kind of said earlier, we're able to prove that there exists a unique invariant density, Q omega, which is it's a density with respect to this capital lambda functional. And we're able to also show that this capital lambda is in fact equivalent, or rather can be identified with a non-atomic Borel probability measure, we'll call it nu omega, which is supported inside of the survivor set. Okay. From here, in the usual way, we can define our invariant measure mu omega to just be Q integrated up against nu. And its invariance in the following sense. We're also able to show that this measure mu has an exponential decay of correlations, both forward and backwards. Here we've just written the forwards. And then it's also an equilibrium state. But first, let me try to answer my two questions real quick. We can define the expected pressure in the open or closed system to be just the integral of our log lambda omegas. And then our escape rate is just going to be minus the limit 1 over n log measure of the survivor set at the nth level. What we're able to show is that the expected, or the escape rate for both the closed conformal and closed invariant measures is the difference in the expected pressures, the difference in the closed expected pressure minus the open expected pressure. Now, like I said...
Excuse me, Jason, can you hear me?
Yes.
Yeah, you have 2 more minutes.
Yes, I only need one of them.
All right, thank you.
So we're able to show that our open invariant measure satisfies this variational principle and is in fact a relative equilibrium state for the system, where this variational principle, the soup is taken over all the T invariant probability measures, which are supported on the complement of the whole. Okay, and the last thing is that we're able to prove a Bowen's formula for the dimension that if our map is sufficiently expanding and we satisfy some bounded distortion and some other large images properties, I don't want to talk too much about that, but if we look at the map, little t goes to the expected pressure of the potential minus t log t prime. If we look at that function, then that function has a unique 0, and that 0 is in fact equal to the Hausdorff dimension of our survivor set for almost every fiber. Okay, and with that, I think I will stop here, and thank you for listening.
Thank you very much. Are there any questions? Yes, please.
Hi. I wanted to ask you, Jason, about in your simplified main assumption, you had an assumption on the some sort of contracting potential assumption, the Q1 prime, yes. And how often, if, for example, if G is the inverse of the Jacobian, can this be satisfied, or what type of potential satisfy this kind of thing? Can we check it on explicit examples?
Yeah, so for the most part, we looked at geometric potentials, which were of the form kind of minus t times the logarithm of the derivative, specifically because we were looking to prove this dimension result that I talked about at the end. But in our paper, we have large classes of examples where we check this for you know, the usual potential as well as these geometric potentials. But we give in these simplified main assumptions, we give also a number of kind of results that allow you to check these assumptions much more easily.
Thank you.
Any other questions? If not, let's thank our speaker again.
Thank you.
Everybody knows you. No, let me still announce you. So our next speaker is Jean-Pierre Eckmann. The title of his talk is The Late Feigenbaum's unpublished book on reflections on a tube.
Okay, thank you for letting me talk at this very last thing, and I hope it's less complicated than maybe it's a good way to give some tribute to Mitchell Feigenbaum. So he wrote a book of about 300 pages. It exists in the form of some text file and figures which I rearranged into a publishable form. And I summarize in 15 minutes what's in this book. So the book is about the study of anamorphs. This is the thing you see here. So does this work? Yes, so you have a cylinder, that's the tube, and then you draw something in the plane, and you ask, what do you see? That's the, okay, so it's nothing about period doubling or the like. So you will see that this is an interesting problem, although it seems elementary. So here is a drawing from his book. This is the geometry of the rays on the tube, so I hope this works. So you start at S, a ray goes to the cylinder, is reflected by normal reflection, and goes then to the eye of the observer. So from every point S, rays go to the tube, and you reach an observer at O. But you shouldn't, probably if you have played games, then usually what people do is the other way around, but that's wrong. Okay, so now what matters here is that the eye gets many rays, you know, because the eye has a certain opening, and therefore it has to interpret the signal it receives. The fact that we have two eyes is irrelevant here, but is discussed at length in the book. So Feigenbaum insists on the well-known fact that what is detected are caustics, not individual rays, and because the intensity of the caustics is maximal. Therefore, the image must appear inside the tube, not on the surface, because if here is the source, this is difficult, if here is the source, then the rays go to the cylinder, which I show here in section, and then the caustics is where you saw it. So now I want to spend a few slides on Feigenbaum's calculation, which is one of the many calculations, and Kemonu Gunaratne, who was Feigenbaum's student at the time, helped me in this. So the ray field emanating from the source S at the distance R, oh, this is painful. Is this easier? No, not really. Huh? Yes, so the source is at a distance r from the center of the cylinder. This is a two-dimensional ray field, and we parameterize the horizontal part by an angle alpha, which is shown here. Why doesn't it go where I want? And another angle beta, or the height along the cylinder. The two angles are perpendicular, but he can also do the calculations when they're not perpendicular, then it's more complicated. Note, and this is important, that he doesn't look at the eye so far. So here is what I call high school algebra. So here is here is the source S. It goes to the cylinder which at the point P and is reflected to an eye at a position E. And there are many angles in this drawing. What you have to understand is that all these angles are related. If you know one of them, you know the other. So there are formulas which are called the sine laws. So the important points are S, P, and E. And another thing which will appear periodically is this distance between S and P. So with these parameters, you can express everything. So maybe it's easier if you just read what's written. You choose the incoming direction, the outgoing direction, and the tangent of the elevation. And the outgoing ray then is somehow, let me show it here, is a contact point and a parameter S on the ray. So the clever thing, which is maybe not Feigenbaum's invention, is that it's useful to write the points in the plane in complex notation. So x, y is a complex point, and then z is the vertical direction. So now, if you know the rays, then the caustics are given by the variation, that the variation of r is 0. And I want to express it in phi, t, and s, where phi is basically the scattering angle, not quite. So this leads then to 3 equations, because it's a 3-dimensional problem. 2 are in the complex plane, and 1 is in the real plane. So I write them in the next slide in real notation, and you see that there are 3 equations, which you believe or don't, in which there you see the phi, the t, and the s. That's along the ray, and the horizontal angle, and the vertical angle. Up to this point, everything is quite simple, and now comes Feigenbaum's insight. There are, in fact, several solutions to these equations. The first case, which he calls the caustic H, happens when the phi is not 0. Well, then the other factor has to be non-zero, and this implies something, and then we must have the t equals 0 because this is not 0, and then you substitute into the equation for r, which I wrote again, and one gets a caustic point, which is given by this formula. And what you should note is that in this formula, t appears linearly. So if you move your eyes up and down, the image moves with you up and down. That's what this means. Now, there is a second caustic. On top, I have just repeated the 3 real equations. And the second caustic is now that dt is not 0. Then dsp determines s. And then you find another caustic point. And this is a new caustic point, which, in my opinion, nobody ever noticed. It's given by this formula, and now you see that t times dsp minus dsp times t is 0, and so this second caustic point is in the plane of the drawing. So there are 2 caustic points, one in the cylinder and one in the plane. So there is a third case, which I don't discuss, which is ray tracing. That's when both d phi and dt are 0. So now the question is, where does the image actually appear in the tube? That's what he calls the visuable surface. It's a complicated surface because you somehow have to invert the problem now from S to E, because the I determines what you see. And here I show on this line the point H, where is this caustic in the cylinder. So you have to invert this relation. And here there's a drawing by Mitchell of how this looks. So what you see, and it's clear, that if you want to show something on the cylinder, you have to map this something on this negative curved surface. So now comes what I find even more interesting, namely, so there are 2 caustics shown here, right? Here is the I, here is H, and here is V. Well, which of the 2 do you see? And I will tell you now that it depends. So the human choice is determined that Feigenbaum notes from the calculation that there's a certain unsharpness depending on whether you look at H or at V. So if you look at H, that's this drawing here, and this is a photograph focusing exactly on H, you see that the image is more unsharp in the vertical direction, and if you look at V, the image is unsharp in the horizontal direction. It's a calculation, it's a few pixels, but cameras and zoom tabs cannot reproduce the effect, but I made a hologram in which you see the effect very well. So now, this is what Feigenbaum discovered, and I tell you, you should try yourself. Usually people see the H caustic, that's the one inside the cylinder, but if you turn your head, you tilt your head like this, then you see the other one. And the question is, of course, why? And this is, you see, let me be pedagogical, right? I think what I like about this kind of mathematical physics is that it leads to new questions, right? Anyway, so what you find out is that this is well known to your ophthalmologist, because if you see not very sharp vertically, you don't correct, but if you see not sharp horizontally, you have to correct. So this is well known. So the brain prefers vertical unsharpness in front of horizontal unsharpness, and that's the reason you see this effect. So what, in fact, it's more complicated, and do I still have time? Yeah. It's more complicated because you don't see really the image of a fixed object, because even if you look with only one eye, I forgot to say this effect works with one eye. You cover your eye, you turn your head. So in addition to focus, the eye brain has to resolve an ambiguity of what it's seeing. It doesn't see an object. Okay, coda. So I think it's typical of Mitchell's thinking that, having understood the example of the tube, which is quite easy, he continued to study vision in several directions, of which I just mentioned the most important. For example, is the human eye good enough to see these small differences? You know, it's only a few pixels. Are fish eyes better? So he has a very long chapter on fish eyes, which explains why fish eyes don't need an iris. Another question which he doesn't answer is, why did evolution do such a bad job in the 500 million years since animals left the water? So the fish eye is much better than the human eye, because it's just a glass ball, basically, with an index of refraction, which changes a little bit to the center. Now, another intriguing question, which I don't know the answer, and he didn't, is there an evolutionary advantage of preferring vertical astigmatism? You know, maybe if you chase in a plane, or I don't know. And are there other instances of HV caustics? And he enumerates a few. Conclusion. This last work of Feigenbaum has opened a new way to think about vision and perception. His pertinent and precise way to ask and answer original questions should be a model for all of us. Perhaps the best way to give tribute to his work is to pursue those problems which he left open. These problems could go from the mathematics of general two-dimensional caustics to the connection between evolution and the physiology of vision. And let me finish with propaganda. So this book is prepared, but it hasn't appeared yet for reasons, complicated reasons. But I wrote another paper. In the meantime, I wrote a paper which is called Broken Pencils and Moving Rulers, is this title, in the American Journal of Physics, and it's in print. So you can do this experiment at home. Do I still have time? Yeah, 1 minute. Okay, you can do this experiment at home. You see here a container filled with water, and you put a ruler on the back. and you look on this container very flat. So you put your eye here, and you look horizontally into the water. The water goes all the way to the rim. And now what you do is you turn your head, and then the ruler will come towards you. Now those of you who go on vacation in the south and go to a piscine, sometimes there are rods going into the water. Just tilt your head and you will see that this rod will also come towards you. Thank you.
Thank you very much. Are there any questions?
Yes.
So could you say a little bit more about why our fish eye is better than human one? Or?
Yeah, no, I mean, first of all, you know, those who knew Mitchell know he does an explicit calculation. There is a measurement of the index of refraction inside the fish eye. And it varies a little bit from the inside has, I forgot, a higher or a lower index of refraction. But it's just like an onion, spherical shells. And he shows that, in the book, he shows that if you, these maps, you know, raise up to 5th order onto the retina. So that's why the fisheye are much better than our eyes. Our construction is very bad because we have this, I don't know, the glass body or whatever it's called, plus a lens. And that's not a good construction, and that's why we need an iris to, you know, to adapt for sharpness and things like that. So, as I said, you know, the book has 300 pages. I just chose the most spectacular thing, but there are many, you know, connections with other things.
Any other questions? Go ahead.
What about the cylinder? I mean, what about the cylinder? Is that
the what?
The tube, right?
Yes.
Why a tube? Is there some?
No. So you can also do it in the water. He also did the calculation. No, the tube, as I said, what makes it easy is that there are two axes which are perpendicular. He does the calculation for general axis, and then instead of, you know, d phi and dt, you have a matrix, a 2x2 matrix, and he shows how you invert it and so on and so forth. Now, with Gemunu, we are trying to find other examples where you have the you have always two caustics, but there are certain conditions which you have to fulfill for this to be visible. So, for example, already Michael Berry studied what happens when you look at the sphere. Well, you know, the problem was that Gemunu was looking for a year for a good sphere. And then the distance between the two images is small. In the cylinder, it's large because one image is sort of behind the cylinder and the other is thing, and you have to take the right diameter so that the eye, you know, has to refocus. All these things are. So the water is an easier calculation, and also the experiment is very easy to do. So that's why I wrote this American Journal of Physics paper, so that people can, you know, explain it in a school, for example.
Okay, any other question? If not, let's thank Jean-Pierre again.
And I want to thank the organizers for organizing this session. Thank you.
Yes, so this concludes our evening session. So the organizers would like to thank all the speakers for contributing very nice talks, and everybody in the audience for coming this evening. Thank you.